All right, so we're moving on to 3 dimensions today. Excitement, excitement.
Were we already found in 3 dimensions?
3 dimensions. Oh, 3 dimensions in the domain.
Yeah, double integration.
Hey, double integration is 3 dimensions.
No, you're integrating over 2-dimensional
But in the
regions.
aggregate.
Today we're going to integrate over 3-dimensional regions.
Oh, can you draw down the board, please?
I will.
One question. On the double integration, and we finish it and we get a number, what are the units? Is it
That's a good question. What are the units on F?
Units squared.
units cubed?
I mean, what is, so it depends what the application is. When we start doing physics applications, we're going to have different units than if you're just doing, find the area under a function, I mean the volume under a function. So the F would be Z equals F of XY, so it would have units of units, or feet, or meters, and then each area of rectangle you multiply by has units of square meters, so you're getting up with cubic meters.
Okay.
But if F is density, that would be something like kilograms per square meter,
Yeah.
and then you multiply by square meters, and you add those up, and you end up with kilograms. So the units are going to depend on what the physical problem you're doing is.
Are we going to use units, like specific units a lot in this?
No. Should we? Probably yes.
But that would be too practical.
Don't scoff, we're going to do some practical stuff.
Right.
All right, so for the record, I told you guys on Friday that we would have a theorem that said it's legitimate to compute a double integral in terms of iterated integrals. So I'm going to state the theorem, and then I'm going to go on and we're going to just keep moving and do more examples and do 3-dimensional stuff, and then I will come back and prove the theorem either tomorrow or Wednesday. So here's the theorem. And it's called Fubini's theorem, and there's a Fubini's theorem. If you look on Wikipedia, you'll see a far more general theorem than this. So it holds with more general notions of integrals than we're working with. It holds with things called Lebesgue integrals, which some of you will find out about eventually. I'm going to state the easiest version of the theorem that's good enough for everything we're going to do. It has more hypotheses than you will find if you go look online. So I'm just warning you about that. All right, so here's the theorem. And I'm going to state it just in 2 dimensions, but it holds an end as well. And I think you'll find the general case even was stated in the book, but I'm not going to try to write down that notation. Okay, theorem. Suppose f is integrable on a rectangle. And let's say the rectangle, this always confuses you guys, but let's say the rectangle is specifically x going from A to B and y going from C to D. And what I want to address is, when is that integral of f computable by doing the iterated integrals, which is what we were doing on Friday? Well, then I'd better make some assumption that the iterated integral exists. Okay? So suppose, moreover, that the integral from C to D of f of xy dy makes sense for every x. So this is the cross-sectional area where I fix an x, all right? So I've got my rectangle, and I'm considering fixing an x and taking the area under that slice. So suppose that this exists or makes sense for every x in A, B, and that net result, that function of x, can be integrated from A to B. I mean, this could exist for every x, but not be an integrable function of x when I'm done. But I'm going to assume that you can in fact integrate that function. Okay, so again, I'm warning you, if you look on Wikipedia, you'll find far weaker hypotheses than this. But then the conclusion will be that the double integral of f, which is defined in terms of our infs and soups of thingies and thingies, equals the iterated integral. Okay, so that's going to allow us, with these hypotheses, to say the way we're going to actually compute these is by doing these iterated one-dimensional integrals using what you know from Calc 2. Really, it would be nice to know that you didn't have to do it in the order dy dx. Maybe you'd rather do it in the other order. So what do you think we should say?
Similarly, the work for the
We'll put this in the middle of everywhere.
It's a good draw. I've always been impressed with your ability to draw a three-dimensional graph.
Similarly, if what?
If you do like b,
So we
a,
want to
c,
just
Switch, right?
Okay.
And we say the integral from a to b of f of xy dx exists for every y, and then the integral of that exists so now we're doing the other slices, fixing a y and taking the area under of the slice where you vary x. So if this area exists for each y, and you can then integrate that function dy, then what do you think we should say? The integral of f likewise equals this. So in particular, if all the hypotheses hold, what does that allow you to do? Right. So you can't just say, oh, I can always turn this into this when they make sense. You need the additional hypothesis to do that. Of what?
That the single integrals exist for all x's and for all y's.
No, suppose each of these makes sense, which means that makes sense and that makes sense. And suppose this makes sense, which means this makes sense and that makes sense. Can I say they're equal?
Yeah.
What you're pointing at that.
Double.
The double integral. So you have to know in addition that integral of f makes sense, i.e. that f is integrable. So we're going to actually play around with weird examples at some point later this week, and you'll have something in homework about it too.
So f cannot be integrable, but you can take the double integral?
Yeah. No, say again.
F,
This could fail,
yeah,
but this could make sense.
yeah.
Iterated integral.
Why?
It can happen. So we're gonna talk. All right. So let me finish the statement. So in particular, if every hypothesis holds, then the integral of in one order equals the integral in the other order because they're both equal to the double integral. All right, so I'm not going to do this today because I want to do more concrete examples. But how many, to get out your combinatorics hat, how many possible scenarios do we have?
You mean as far as,
This could exist or not.
right,
This could exist.
Or not.
This.
so
Could
eight.
exist or not.
So how many possible? 8.
Both of those exist? Do we know the double integral exists?
No.
If they're equal, do we know the
No.
integral?
So you have 8 possible scenarios, and we will actually make a table of them either probably tomorrow.
So we're tabling that another day?
We are tabling it. So that's the end of the statement of the theorem. So discussion of examples and proof to follow, but not yet. But I just wanted to state this so that you know there is a theorem and you can use it. And again, it works in 3 dimensions, 5 dimensions, however many, but you have to make the appropriate assumptions on the nesting of the various integrals. That always has to make sense.
So if there's 3 dimensions, how many?
You tell me, how many different possible orders? This is an easier counting
2 to
question.
the 4?
No, if I have 3 dimensions, how many possible iterated integrals could I have?
6.
It's 6.
So like
3 factorial, right?
Times.
You have 3 choices for the innermost. We're actually going to do some of this today. You have 3 choices on who's inside. That leaves 2 choices for the variable in the middle, and then the last one is the term.
And then that times 2?
So 3 times 2 times 1 is 6.
But
So
then,
that would be-
but then like the total
2
number.
to the 7.
Oh, no, that's still just 8.
No,
No.
right.
No.
If you're talking about where we got the 8, it's still a question of, does the iterated integral in some order? No, it's not just
Every
eight.
order.
No, it's not.
It'd be 12,
Not
right?
every-
It'd be 12.
That's what, yeah.
Yeah, because you have 6 different possible iterated
And then the
integrals,
double integral.
each of which could exist or not. Oh, so that's 2 to the, no, the 12 is wrong.
2 to the 7, 14.
That's what I said. 2 to the.
Or 2
So it's 2 to the 7, isn't
You
it?
said every even
Wait,
number
but-
of the 6.
Can we leave this alone? Serious
More
question.
possibilities.
What was I gonna say? But, so if we had the 3 variables, that would be trying to solve, does it make sense, like the volume of a 4 space?
Yes.
Okay.
So you can think of it as graphing a function of 3 variables, which means you would put it into 4 space, and then you would be taking the 4-dimensional volume between the 0 plane and that 3-dimensional surface.
4-dimensional volume.
Or you could think about f as a density of an object in 3 dimensions, and then you'd be integrating and getting the mass of that object. So that makes more physical sense,
Can you think of different colors too?
if you want. All right, so let's do some examples today. So I didn't do something like this the other day, so I want to warm up with something simple. Suppose omega is the region I'm about to define, and I want to integrate the function, say, xy over it. And let's say this is the region omega. I got y equals x squared here, and I got y equals x here. And omega is the stuff in between.
That's where I feel like the green line is on the triangle, but not on the YZ plane.
This
Yeah. Like the vertical one. You draw it on the YZ plane.
is in a plane parallel to the xy plane.
He's saying your vertical line touches the axis instead of the edge of the rectangle.
Oh. Thank you. See, I never used to make these mistakes. So, now I'm just too self-conscious about it. All right, back to this. How are we going to do it?
To get double integral?
Well, we're going to do
Or
the
is it-
thing we do where we create an extended function.
Right. So we're going to say, think of this as living inside, say, a square, and then make the function be x, y, and omega, and 0 outside. But we've already talked about how you deal with that, and so I'm not going to pedantically go through that again. Do you want to do which order? Again, this function is going to be continuous, which means the f bar function, when you extend it the way Daniel just said, is going to have discontinuities only along the frontier, which is a perfectly nice set of areas 0. We're not going to keep worrying about it, so we're just going to apply Fubini in this setting and say you can do iterated integrals. Everybody's continuous except on that set of area 0. So, do you want to do, which order do you want me to write?
Y on the inside, right?
Y on the inside? Why do you like that?
Because you already wrote it in terms of Y.
That's right. We already have, well, you have y in terms of x.
Right, yeah.
So you're naturally thinking of this region as being demarcated by functions of x. So let's put x on the outside. X goes from what to what in the whole region?
0 to 1.
0 to 1. And if I fix an x, and I shoot a ray parallel to the y-axis, where does that ray enter the set and where does it depart the set?
X squared x.
Okay. Right, so you're going from here to there, so that becomes the limits on your integral, because down here the function that we were talking about is 0, and the function we're talking about is 0 here, so we ignore them. And then I put in my function, and then you know how to do it. Back to bookkeeping. And at this point, I'm not going to keep writing parentheses, but if it confuses you to think about this, you're welcome to put parentheses there if you want. Luis, you okay? All right, moving up. Let's do the integral of z. Now I'm going to move up into 3 dimensions, where omega is the region bounded below by the xy plane, on the sides by a cylinder. You have so much fun to look forward to. And above, so I'm trying to help here by giving you these shapes, adverbs. That's an adverbial clause, I suppose, phrase.
Preposition. Above is like a preposition, right?
Well, but when I'm saying by, it's no longer, I don't think. Yeah, that's what I was thinking for a while. And above by the plane, z equals y. All right, so our first task is to draw a picture. It doesn't have to be beautiful artwork, but it has to be good enough that you actually can visualize what's going on. Like,
Yeah.
who sliced?
It looks like a
No,
tree
no,
stump,
sorry.
like flat at the
Cylinder.
bottom and curved on the side.
It's like a cylinder that's like
Cylinder.
a PCB pipe that's been like diced at an angle.
So, all right, so I draw a cylinder, and I slice it with the plane z equals y, and notice I'm saying, well, did you have a comment?
No.
It's bounded below by the xy plane, so I'm taking this here as the lower boundary, and so if I think about z equals y, it's going to come up at an angle here. It's going to be a plane, and because of perspective, I'm going to tilt it less than you expect me to. It's going to be a plane that's going along the line z equals y in the yz plane, and then it comes out at you. So I'm not going to obliterate the whole picture by drawing the whole plane, because that will make it harder to see. So when you slice at that angle, what shape do you see?
Round wedge.
It's like a
You
half
if you take a log of wood and you slice it on the bias, you get an ellipse. So you're slicing part, where does it go underneath the xy plane? It goes underneath in the 3rd and 4th quadrants. it's above in the first and second. So you're actually getting half an ellipse here that goes from this point on the diameter of this circle to this point on the diameter. And you're looking at the stuff that's in between that tilted plane and the plane at the bottom. So what does it look like to you?
Like a slice of cake that's in the cup.
So you have a round shape. Will, you remember what we called it last year? Yeah, it's a wedge of cheese. If you take a big wheel of Parmesan cheese, since it's almost lunchtime, and you slice through it, you get a chunk that you pull out. Or a chunk of wood, if you prefer, if you think of this as a tree. It looks like that. So how do we set up this integral? So we will, later this week, we will learn about polar coordinates and use the radial symmetry, but for today, we're just going to work with x, y, and z.
Where does
So it's in the
what we did in the first part come into play here? I'm a little confused by.
What, this?
Yeah.
These are separate examples.
Okay.
Sorry.
Oh. Okay,
Sorry,
that
my
makes a lot
fault.
more sense. I thought I was like.
No, I'm going to do a bunch.
Okay.
Yes, outside.
Who outside?
X.
X outside?
X from -1 to
So let's see. Let's start out. The way you want to start thinking about three-dimensional stuff, you want to say I want to think about, just as here we said, what does X do? We think about taking the whole region and smushing it down on the X-axis and seeing what we covered up. In this case, as Yiming is suggesting, it's reasonably natural to think of this as living over the XY plane, although, as you'll see later when we do different examples, including this one, we could project it into the YZ plane or the XZ plane. But Yiming is saying, let's project on the XY plane. What does this thing project onto? Semicircle, where Y is?
Always positive.
Right. So the projection in the XY plane is the inside of the unit circle above the x-axis. So we're going to work our way again from the outside to the inside. So do you want dx dy or dy dx?
dy.
All right, Yimeng wants dy dx, so I'll listen to her.
Does that actually matter?
It does not, except again, this is a graph of y as a function of x and
Right.
not the other way, so it's a little easier that
Okay,
way.
yeah.
Right, because if you slice this way, it's easy to do that.
Okay.
So we're going to first slice x and say x goes from what to what?
0, 1 to 1.
And for each fixed x, what does y do?
Is it 0
0
to
to 30 of 1 minus x squared.
1 minus x squared. And now comes the fun. For a fixed point in the xy region, you now shoot a ray vertically, or a line, vertically parallel to the z-axis, and you ask yourself,
So
From 0 to 1.
that's fine.
where does it enter, where does it exit?
0 to 1.
It enters at z equals
0.
and exits at
1.
z equals y. And of course, there's a dz. Everybody okay with that? Anybody said no? So, shall I do the bookkeeping exercise, or are you okay for us to go on?
Let's do the bookkeeping.
Yeah.
All right? So, again, you start on the inside, right? We work our way from the outside in when we're figuring out the limits, but for integrating, we start on the inside, of course. What's the integral of z dz?
Z squared over 2. It's y squared over 2.
Okay, so when you do z squared over 2, I'll put the steps in, from 0 to y, you're going to get y squared over 2. Whoops. that.
Cubed over 6.
Hmm?
This will be y cubed over
Y
6.
cubed over 6, I'm going to pull the 1/6 out. And then when I do y cubed, I'm going to evaluate from 0 to square root of 1 minus x squared.
So then it's just that. Cubed.
So I'm going to have 1/6, the integral from -1 to 1 of 1 minus x squared to the 3/2. How do we do that integral?
It would be divided by like 2 over 5.
No, 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 you don't have an
Yeah, because
x.
there's a du.
We go back.
Go back? Go back to whom?
Where is that?
We switch x
Right
and
in
y.
terms of y. I did the x, integrate x before y.
Then you'll just end up with a dy integral with the same thing, with a y there,
Correct.
right? Because it's sort of a pain. So maybe I'm going to quit, but remind you guys how you would continue. Does anybody remember how to do integrals like this? What trig substitution?
Somebody side or good side.
Yep, exactly right.
It wouldn't be the exact same, would it? If we switch-
Well, you switch x and y, but it's going to be the same. It's going to be a symmetric integral.
Why? What, isn't it?
Try it, Jonathan. Just sit down and write it.
Well, that function's even, so shouldn't it be 0?
No, it's double what it is from 0 to 1 because it's even. Yeah, we could hope that symmetry would make, but if you think about the problem physically, I'm asking you to integrate z over that region, that's going to give you a positive answer. If I'd asked you to integrate x over that region, by symmetry would have gotten 0. So we're going to start talking soon about center of mass and thinking about symmetry. That's coming very soon. All right, so the way you would finish that is you would say let x equal sine of theta, or sine of u, say. Now, x is going from -1 to 1. What does u do?
0 to
Pi over 2 negative pi.
Right, -pi/2 to pi/2. And then you would have 1/6, the integral from -1 to 1. Now, we could use symmetry as Daniel's pointing out and say by symmetry you could just do it from 0 to 1. And double it, because we're integrating an even function, and the area under an even function symmetrically from -a to a is double the area from 0 to a. That's good to save a little work. And then now u is only going from 0 to pi/2. And this becomes sine cubed u. Is that right? No. What does it become? 1 minus sine squared.
cosine cube.
Cosine cube.
And it really should be absolute value because we're taking square root of a square. So it really should be absolute value of cosine cube. And then what happens to dx?
du. Oh,
Yeah.
du, you divide it by
Cosine u du.
cosine u.
What's dx?
Cosine u du.
Right, and we'll talk about what d means later this semester. Now, cosine is positive everywhere here. So you say to yourself, I'm okay, and you don't bother with the absolute values. But unfortunately, this is now an integral that I would bet very few people in the room know how to do. So
I bet on one.
here goes on Wolfram alpha.
Double angle.
Can you do?
You have to do double angle twice.
Yeah.
You have cosine. Can you break
So
up
this is
cosine?
probably an integral that a 2260 teacher wouldn't make you do, but a 2410 teacher would. So
Would you do
I will
cosine?
leave you to finish the problem at this point. Would it be any easier if I projected it a different way? Instead of doing it in that order, would it perhaps come out easier if I did it in a different order? So what if I decided suppose I didn't want to put z on the inside. Suppose I wanted to project it onto the xz plane. And I put it in this order. Would that make any difference? So let's practice. Let's see if we can set this one up before we do a few more examples. If I now project this onto the yz plane, or xz plane, sorry. Right, I'm looking at the outer two variables. What do I see when I project that onto the xz plane? So can you visualize it better if I make it the yz plane instead, maybe? Let's do yz. Let's put y here and x here. I think that'll be easier for you to see it. So take that chunk of cheese and plop it back to the board into the yz plane. What do you see?
A triangle.
You see a triangle with z equals y going here, z equals 0 going here, and the vertical line where y is 1. Agreed?
What would the xz plane be?
Well, we'll get there. I'll do it. All right, so you know how to set up the iterated integral to do this. So y goes from what to what?
0 to
For each fixed y, what does z do?
0 to 1.
And then, if you fix a point in the yz region and shoot your line in the x direction, where does it enter and where does it exit?
It's
Plus or minus x squared 1 minus x squared.
No.
square
Something to the positive.
So we're in,
times 2.
we're imagining taking a line parallel to the x-axis and shooting it through this region. It exits there, it enters at the back. What gives you the equation of what it's
X
cutting?
squared plus y squared equals 1.
It's from the cylinder, right? So if you're fixing a y and a z, what are the x values where you puncture?
Square root of 1 minus y squared.
And minus, right?
So they're pretty much the exact same. So never mind.
Yeah,
You use the same exact graphs and form, you just kind of shake them around a little bit.
yeah, I mean, you just have to visualize it in a different order of chopping, as it were. Is this integral going to be any easier?
I mean, can we do that? Is that an even function, 1 minus y? We'll make it from 0.
Well, okay, so let's see what happens. What happens when you do the innermost integral? You get xz, so we're going to get, the change in x is this minus this, so you're going to get twice square root of 1 minus y squared z. You're going to get a different integral, guys. You see it? What's the integral of z dz? Z squared over 2. This is a constant when I'm doing that integral. So the 2's cancel. And I have square root of 1 minus y squared times y squared, right? Minus 0 squared. And then I have to integrate that dy. That's a different integral. Is it any better? You're going to have to do a double angle again. Again, you're going to make a trig substitute. You could do integration by parts, if you remember how to do that. Or, again, now let y equals sine u. And then you're going to end up with sine squared, cosine, cosine. you're going to get sine squared, cosine squared. And that's one step easier, actually, than the previous one. Because this is double angle. This is half of
And sine 2.
sine of 2u squared. And then you have to do double angle to do sine squared again. Yes, you have to review integrals. Jonathan wanted to know what happens if you do it in the other order. We're not going to bother with all 6, but
6?
There are 9.
Oh, 6. Oh my god. I'm sorry. I'll take your probability class.
It should be sine squared cosine, right?
cosine and then another cosine,
Oh, okay.
right? Because dy would be cosine u du, and this is a cosine u.
Okay.
All right, so lastly, what would happen if I did what Jonathan wanted before he said something silly?
But it's 1 minus y squared when you take the square root of that. Y is
But you're changing dy to du.
Again, you have to do, when you do substitution, you have to put in dy du, so you get another cosine from that.
oh, okay.
All right, what's the last order you guys wanted to do? You wanted to do dy, dz, dx. So what's the projection into the xz plane? So if you take that hunk of cheese and you slap it into the xz plane,
It's
Is that a
a
triangle?
ellipse, I think.
Oh,
Half ellipse.
yeah.
this is harder, right?
It would have to be a half ellipse.
So clearly,
Wait, is it not a semicircle?
Is it a semi?
I think it's a semicircle
That's
with
what-
radius 1.
so clearly
So,
you had
It's not a circle.
this segment here
It's height.
Yeah.
projects to be,
The height?
It has a height of 1 though.
Yeah, that's how I want.
gives you a height of 1 here.
Yeah, so it's
So it is a,
This is-
Yeah.
just
And then the radius in your bottom circle is also 1
Mhm.
in the x.
Now, these points certainly stay where they are. So the question is,
Is there a triangle?
Is there a
It's
triangle?
kind of circle.
oh, they're saying it's
no, it's a circle, semicircle.
It's a triangle.
like an isosceles.
now if you take this orange curve here
Think of this.
and you project it into this plane, it's going to be curvy.
Yeah, it's a circle, semicircle.
You're not projecting in the direction of the plane, you're not projecting into the YZ plane, you're projecting into X. So Reese is voting for a semicircle still, is he not?
Yeah, but the height's going to be.
It's going to be 1.
I'm voting.
I'm not sure it is.
Yeah,
It's
that's a
in-
circle.
So we have some votes here that it becomes a circle going like that in the XZ plane, where this blue height is at the axis. That height is the height of the circle there. How are we going to settle this? Besides a duel at 10
You
paces.
see the on the axis, it's 2 on the axis, and then the height is 1, so it's like half of x.
But
When it's right on the axis, and then it's kind of
so
symmetric.
you actually have to use some math at some point and not just try to guess. How would I work with my equations and try to figure out what this is doing?
Going z equals y. So to get y in terms of x, you get y equals 1 minus x squared.
So here, yeah, so what Will's saying is on the right track. We're trying to see what the projection into the XZ plane. That means we want to ask ourselves, for what XZ are there points in the region with some y value? So what do you want to do? You want to take these equations and get rid of y.
So if you substitute, it just becomes x squared plus b squared.
So where do these two things intersect? That's this curve. But if you take this curve and you project it into the XZ plane, what we're trying to do is get rid of y. So the math word for that is eliminate y. You can hire a hit x to go and eliminate y.
That doesn't make sense.
So what do we get for the equation? Well, y becomes z, and you got x squared plus z squared equals 1, and Reese wins. Of course, you've still only got y greater than or equal to 0. I'm sorry, yeah, or z greater than or equal to 0, so you're still going to have a semicircle. So this green curve in the xz plane is exactly a semicircle.
Enjoy this moment, Reese.
Now, you could hope that this is going to come out an easier integral. Let's try. I don't hold out much hope, personally. So I'm going to stay under here where I am. So in that order, what are we going to have? All right, slow down. I got to catch up. Start on the outside. X goes from?
-1 to 1.
For each fixed x, z goes?
0 to 1.
0 to 1, square root of 1 minus x squared, and for each fixed x and z, what does y do? I didn't draw that in the picture. That's a new color. So you're now going to take a point in this green guy and shoot a ray in the y direction. Where does it enter? Where does it exit?
On the y equals
Exits at 0.
0 to z.
Where does it enter? Y equals z. And where does it exit? No.
1.
No.
So square root of 1 minus x.
Exiting at the cylinder, so it depends on x. So it enters at y equals z, and it exits when it hits the cylinder, which is y equals square root of 1 minus x squared. This is why you actually have to draw sketches, and you can't just think, oh, I can look at the formulas and just do it in my head. You can't. So the question now is, there's a z we were integrating. Is this problem any better, or is it worser?
It may cancel, it may not cancel.
Well, let's find out. What's the innermost integral going to do? Integral of z dy. So I have to do z times this minus this. And then integrate dz, and then integrate dx. We're going to end up with pretty much the same integral, I think, that we had before. So the inner integral, we're going to get a z squared over 2 times the square root of 1 minus x squared minus the integral of z squared. And z goes from 0 to the square root of 1 minus x squared. And then I integrate dx. So what do you see?
1 minus x cubed, 3 halves.
Yeah, you're going to get square root of 1 minus x squared cubed minus square root of 1 minus x squared cubed. But you have a 1/2 minus a third. So we're back to our original integral. Didn't help.
Now what happens if we moved it?
However, you can start to see that there is a little bit of artistry to conceptualizing what things look like and how you convert the integrals in different orders. So I wanted to do some more practice with that. So there's actually a couple problems in the book that are, you're going to have some web work like this too, starting on Wednesday, by the way. So let's do one, and then we'll do another, a little bit more tomorrow. So what am I up to? Number 4, huh? 3. my watch wrong? I have 1.5 after.
That's about where I am.
All right, so here's a problem that I'm picking at random from the book. It happens to be number 12E. And it says, change the order of integrals, of iterated integrals. And basically, we don't have a particular function in mind, but we want to rewrite this iterated integral as an iterated integral in the order with, I believe, y on the inside, it says.
So we gotta find our region.
So you've got to decide what the region is, and then you've got to figure out how you redo the iterated integrals. So we may not quite finish this, but let's get started.
X goes
So you have to start with this and say, what does the region look like? So in the xy plane, x is doing what?
from 0 to 1.
And for each fixed x,
0 to 1 minus.
so what should I draw in my picture here?
You have a C,
It's like a triangle.
Y equals 1 minus x. What,
it's a triangle.
but I need a particular, so tell me what to draw.
Y-intercept is
Starts with
1,
1.
and then, yeah.
So it's going to be this triangle. And this is the line x plus y equals 1. Everybody agree? Now comes the part that is hard to draw. Z equals x plus y.
Well, it's gonna be 1 along that line.
Well, it's just gonna go 0 to 1 on the x and y intercepts.
It's gonna go 0 to 1 on the x, y, and that's gonna be 1 over the line of that triangle, the outside line.
Ah,
Yeah.
so what you're suggesting I draw, it's
Shoot a line.
rather than trying to draw the plane and get the perspective all screwed up, what you're suggesting I do is say, here, if I, over this point, I'm going up at an angle until I get to the point where z equals y equals 1. Same thing over here,
Then
And
it's a straight
then-
line.
and actually over this green line, you actually have a straight line directly above it. So this, the perspective is difficult, and I don't, you know,
Wait, are you
you
saying-
might do better than I will do drawing this. This is a wedge coming out at you, tilting up. And the region we're looking at is bounded below that tilted plane. So we're looking at z's that go from here to the plane. So you're starting your chunk at the xy plane, and you're going up until you hit this tilted triangle up there.
Okay, yeah, that makes sense actually.
I think it would be easier to look at if you drew a second picture with with the perspective looking in the opposite direction.
Yeah.
That would be easier to visualize, like after you get the basic points down.
So when you say the opposite direction, what are you suggesting I
Look
You
at it from the negative.
do? Do you want to come draw?
sure.
Well, look at the time.
We're sort of out of time. Let's pick up with this tomorrow. Oh, you won't be here. How convenient. How convenient.